cups and executive processing in smokers. Please.
All right, so yeah, I'm going to present some of our recent studies, particularly this CYP2A6 genetic variations, and describe how this genetic variation changes striatal-cingulate circuits and executive functions. All right. So, yeah. By the way, I'm from the National Institute on Drug Abuse, so we do a lot of addiction studies. So just give a little bit of background of the addiction. So this is kind of a survey for substance use in the USA. And what we can see here is basically ask a very simple questions. In the past 30 days, did you use any substance, alcohol, cigarettes, and illicit drugs? So surprisingly, you see, those are the high school, 12th grades, those are high school seniors. And 10th grade, high school sophomore, second year. And 8th grade is the middle school in the USA, right? So ask them, did you use any kind of alcohol in the past 30 days? See, quite a bit of, let's say this is the latest 2012. See, about 40% of people used alcohol. Well, not surprising, the high school kids, you know. But look at the cigarettes, about 20% used. And even for illicit drugs, something like cocaine, marijuana, heroin, about 20% used. That's a little bit surprising for me. But anyway, so that's kind of a situation in the U.S. You know, even middle school, high school kids are using those substances quite a bit. And look at the costs for the healthcare for those substances. It's quite a bit. You know, it costs a lot for the government. And the overall, including Medicare and also including some of the car accidents and inability to work and so on. So the total cost for the U.S. government is 60 billions per year. So that's a huge number. And actually that's probably the number one cost for any kind of disease, if we consider the addiction is a psychiatric disease. So that's a very serious problem, at least in U.S. and in China also. The addiction is growing rapidly in recent years, right? So just for those not doing the addictions, I just give a little bit of definition here. So what is addiction? So addiction is a disease, a psychiatric disease. So manifests as a compulsive drive to seek and take the drug. Regardless of severe adverse consequences, and also characterized as a repetitive relapse. So people can stop using, but after a while just use again. So that's kind of a definition for the addiction. So particularly for nicotine, for example, nicotine is able to producing a lot of things. For example, tolerance. For example, people smoke like 5 cigarettes per day, and after a while it's not enough, and then 10 cigarettes per day and 20, for example. And also can produce the physical dependence, and so you have to use it, otherwise you feel very bad, and have withdrawal symptoms upon stop using, such as irritation, anxiety, and depression, and so on. So again, here's another graph to look at the percentage of population using the cigarettes. So look at from 1960s, about 40% people are using, and along with some of the development of some of like a nicotine gum, so you can chew the gum, and to reduce the use of cigarettes, and also have a patch, and some of the drugs recently developed to reduce the smoking. So it's decreasing from 40% in the 1960s to about 20% in the early 2000. But it looks like it stopped there. So we hope it will drop off more. For example, we estimated that like 2010 will reach to 12%, but it didn't happen. So it's pretty much a flat, 20%. But if we look at the situation in China, I think now pretty much 40% now. So it's a serious issue for health. So yes, yeah.
Just looking at these statistics here, right?
Uh-huh.
I mean, what's your take on introduction of nicotine patch and the lozenges? They're not really very effective in that case.
Yeah, it's helpful, in some cases, but yeah, I mean, all the treatment, successful rate is about, 30%, 20%, 30%. So that
This decline seems to be pretty much public health, right? I mean,
it's I agree. It's because your smoking would cause cardiac vascular disease and so on. So it's a public. Not very sure. I mean, those how relevant to those methods developed. Yeah. But still, so if we look at nicotine, and so if we smoke, the nicotine gets into the blood, then it's metabolized into cotinine, right? And so what's the key substrate of that? So this gene, the CYP2A6, we call CYP2A6, this gene just controls the producing of this enzyme, and this enzyme in the liver. So when nicotine, just goes through the liver, it gets metabolized from nicotine to cotinine about 60 to 80%. So that's why we are kind of interested in this gene, because this genotype may have impact on the smoking. So if we look at this CYP2A6 gene, and can divide it into like 3 subtypes: normal type, intermediate, or the slow. So sometimes we can combine this intermediate and the slow, combine them as a reduced. So basically, they reduce the rate of the nicotine metabolism. So you can imagine for those people, nicotine will stay in the blood for a longer time, right? So some early study look at the metabolism rates. This is a normal genotype, so like 100%, and intermediate 74%, and the slow type will be reduced to about half. And look at the behavior for this genotype. So sorry for this kind of small, but I just want to show you. Here is a cigarette per day. So how many cigarettes are used per day? And if we look at the reduced genotype, they use less compared to normal. So as I said, because their metabolism rate are reduced, so the nicotine can stay in blood a longer time, and they need less cigarettes per day. And also, if we look at this FTND is dependence, it is a measure of the nicotine dependence. So for those with a reduced gene, the dependence level is also lower than normal. Okay. So let's just kind of back one step and look at the status now. So what do we know and what do we don't know? So we know this gene, at least this CYP2A6, can alter the enzyme that is active for the metabolism of nicotine. And we also know this gene can affect smoking behavior, such as smoking cessation, relapse, and response to the therapy, and so on. However, what we don't know is neuromechanism underlying this behavior and this genotype. So, okay, so that's that's about like 2 years ago. We started doing this study, and we have a couple of hypotheses here. So first, this genotype would differentially shape the functional connectivity of the brain networks in smokers versus non-smokers. And the second hypothesis is this genotype will differentially alter the executive functions actually related to this network changes. So then we designed this study. So this basically we try to look at the interaction of this genotype and also the environment. Environment is smoking or non-smoking on the brain intrinsic functional connectivity. And we also look at this interaction and during the executive processing, such as go, no go, and some reward processing. So yeah, so here are the subjects. Just want to let you know, this is another kind of a design at the beginning. So basically, we came up this idea, then we look at our database. So we, in the past, 10, 15 years, about 15 years, I'm at NIDA. So we collected about 1,000 subjects, and we have about 500 or 600 of subjects. We have a GWAS. So it's kind of so we kind of retrospectively look at the data. So that's the data we available a couple years ago when we came up with this idea. So here we have 158 subjects, and this breakdown to the different genotypes. It's about 20 or 25 subjects, and for the non-smokers, and we have similar numbers, a little bit larger maybe. The imaging is 6 minutes resting state function MRI, and and in the image processing, it's pretty much a standard pipeline, so I don't want to go through details. So just want to emphasize a little bit of the functional connectivity analysis. So here we use the so-called functional connectivity strength, which is pretty straightforward. Basically, it's average functional connectivity between one voxel, for example, here, and the other voxels in the gray matter. So basically, it's a summation, or it's the average of the connectivity, for one particular node to any other nodes. So in this way, we can do whole brain voxel-wise or node-wise analysis, right? So if look at the demographic, and pretty much, we try to match everything. The age, the sex, race, years of education, and so on. So the important, we see some significant differences in the cigarette per day, CPD. So you can see again, the slow type use less cigarettes, as I showed you at the very beginning, right? So that's pretty much as expected. And in the statistics analysis, so we used pretty much also standard two-way ANCOVA. So it's like a 3x2 ANCOVA, and we have 3 genotypes: normal, intermediate, and slow. And then we have 2 this kind of environmental factors: the smokers and non-smokers. And we put the age, gender, IQ, education year, and carbon monoxide as covariance. So here's the main results. So as I said, we try to look at the interaction of the gene-environment interaction. So here's through the whole brain search. So we we found 2 regions showing this interaction. And one region is in the ventral striatum, and another region is in the dorsal ACC. So if we look at the ventral striatum region, the pattern is something like that. So for the non-smokers, they are pretty much flat here. So not much. This gene doesn't have much influence on people who don't smoke, because that's to control the enzyme to metabolize the nicotine. But for people who don't smoke, so it doesn't matter too much. However, for the smokers, we see quite a bit of differences here. Basically, the slow genotype have a lower, significantly lower functional connectivity strengths here. And similarly, in this region, dorsal ACC, and not much difference in the non-smokers, and significantly reduced in the slow type. So then we also look at this imaging measures with the relationship of this imaging measures with behavior. So again, this is FTND is a measure for nicotine dependence. It's a measure of the severity of the nicotine dependence. So what do we see here is this functional connectivity strengths in those 2 regions are negatively correlated with the FTND. So suggesting for people with less connectivity strengths would have a stronger dependence level for the nicotine. All right. So yeah, since we analyze this with functional connectivity strengths, which is a summation or average of functional connectivity from one seed to the rest of the brain. So we want to look at more specifically which region really affected the connectivity. So we kind of look just using these 2 blobs from the main analysis. We did a post hoc analysis to look at the individual connectivity circuits. So, for example, from this dorsal ACC region, and we see pretty much the connection to the insula, for example. This is reduced, and again also from ventral striatum, and we see the circuits to the insula kind of reduced. So then we try to interpret that, and we know the striatum has strong connections with the frontal regions and the cingulate regions. This is a monkey study actually. It's a review paper by Susan Haber. It's from a monkey study actually, from a monkey tracing study, and she found a lot of connections, anatomical connections from striatum to the frontal regions. So what we can see here is maybe the greater amplitude or longer duration of the nicotine in the brain may mediate this reduction of functional connectivity strengths in the striatal cortical circuits. And this gene may mediate smoking behavior by changing this brain circuits. So yeah, that's the main story. So we were, when we saw that those data, obviously we were very happy to see just a single gene, can change the brain, change significantly some brain regions, some function, some connectivity properties, and also related to behavior. So yeah, we were pretty happy, but we just wanted to just move one more step to look at these interactions during executive processing, just because the resting state, functional connectivity just tell us how they are talking each other, but we don't know exactly how they deal with the brain function, the brain tasks. So fortunately, we had a couple of tasks performed for those subjects. So we have a no-go. It's inhibitive control. And also we have a monetary incentive delay, which is a reward task. So then we look at the functional response during those tasks. So just for those not familiar with this task, as MID is a task developed also at NIH, and many years ago, probably like 15 years ago. So this is basically, you probably don't need to know details, but this task is pretty much activate the reward regions such as ventral striatum. So you will see kind of a Christmas tree light up in the ventral striatum. It's a very effective task. And the other task is go no go. People probably would more familiar with this. So just have a series of letters, for example, X and Y, and in some cases you have to stop the pressing. But most of the time you keep pressing, and sometimes you have to stop. It's an inhibitor control. So yeah, all right. Yes, so this is a subjects. It's kind of a subset of those resting state, because as I said, this is a respective analysis of the data. So not all subjects have this task. So it's a subset. Some group are kind of small. It's now reduced to like a 10, 15-ish. Yeah, that's kind of a, for genetic study, it's pretty hard, to dealing with this kind of number. And actually, we got a lot of criticism from reviews for this study. Yeah, otherwise, probably going to publish a little bit better, but it's eventually published in Biological Psychiatry this year. But anyway, so yeah, for subjects, here we have 43 subjects, and we break down to to normal and reduced, and you can see we take off the intermediate, because intermediate, the number is like a 5 or 6, so it's pretty hard to. Yeah, so imaging processing is very standard pipeline, and statistical analysis is also very, very standard general linear models. So okay, just want to show you the results here, and yeah.
So when did the last time a smoke before the community scan?
That's a good question. Yeah. Actually, we did it twice. For the resting state, we did twice. One time is we call sated, so they just smoke as normal, and second time is 2 days after the abstinence. Yeah. So we have I showed all the data I showed is for the first study. Yeah. So okay. So here. So if we look at the interaction, the gene environment interaction here, so for MID task, we look at the ventral striatum area, so we see this kind of pattern. It's very similar to the resting state connectivity pattern. And for the go-no-go, and that's the inhibitor control task, so we look at dorsal ACC, basically also very, very similar patterns as we see from the resting state. It's kind of give us more confidence, the gene would not only change the resting state connectivity, but also would change the functional response to these tasks. So okay, so now, as I mentioned at the beginning, so now we kind of have a bridge to linking this genotype to the behavior. And I just summarize the study. So basically, a strong gene-environment interaction in the cingulate and striatum, ventral striatum network was demonstrated. And the ability of this network in processing reward and response inhibition was compromised differentially in the smokers versus non-smokers. And so this suggests different strategies for the treatment of nicotine addiction is needed because you can see the 4 smokers with different genotype, and their behavior are quite different, and their brain circuits are altered differentially. And finally, this striatal and cingulate circuits may be used as an imaging biomarker. So this is more kind of an objective index to monitor the treatment, for example. I just want to thank, at NIDA, the Sufan Li is a postdoc, did all the work, and also University of Toronto, Rachel Tyndall and her team did all the genetic analysis. Yeah, thank you very much. Yeah.
Questions?
So what's the downstream? Where are you guys headed with this? I mean, what's the plan using this kind of data?
Sorry?
I was wondering what your plans are in terms of thinking about this as an intervention of some sort in the community, right?
Yeah, that's something we're thinking about. From this kind of the gene environment interactions. For example, during the treatment for reduced genotype, because the nicotine level in their blood is a little bit higher and takes a longer time. So the nicotine replacement therapy may not help much. So that's probably suggesting needs to use some other pharmaceutical treatment. So that's something we are thinking about.
Can I ask you, if you look at the age of starting smoking on your group?
Sorry, the age of the.
So these studies, so if you separate them into.
Yeah, let me show you the larger table. This one is that the age. Let's see. Yeah, it's kind of 30.
No,
I'm sorry.
Age when they started smoking.
Age of yeah. No, that's a good point. That's a good point. Yeah. So the genotype would also affect the initiation of the smoking. Yeah. Obviously in this study, as I say, it's a retrospective. Not very sure of those. But for new studies, definitely we'll put the age of start as the important factor.
Kind of back on the question of the functional connectivity strength. Did you do local signal regression in that analysis? Because you average the whole brain, if you have a negative and positive correlation to average.
Yeah, we didn't take off the global signal. Yeah, it's controversial. I know. So actually we tried. I think we tried both, and the results are pretty similar. So it's kind of just prepare for the reviewers' questions like you. But it's a controversial issue. So most time we don't do the removal of the global signal.
You could have also done the average of the absolute values to see just overall.
Right.
As an exploratory.
Right.